Hi everyone, so here we are at section 2.37 talking about students' t-distribution. Now Bishop is going to introduce this distribution in a really interesting way that I hadn't seen before, so we'll be going through it together for both of us for the first time. But I thought it might be interesting to kind of just start off with discussing the context in which you and I have seen the t-distribution before, most likely, which is statistical testing, and we'll see that it kind of connects a little bit to what Bishop is going to talk about. So it might just be interesting in that sense. Okay, so you've probably heard of something called a t-test, and this is a frequentist test for determining, in the simplest case, whether your data has mean zero. Okay, so you assume that your data is coming from some normal distribution. So you have independent observation of normal distribution with mean zero and variance, and the key thing is you don't know the variance. So we've got observations x1 to xn, and we can compute their mean, right? So let's produce their mean, which is going to be equal to 1 over n sum on xi. Okay, and now the idea is that each of these xi's we're going to assume is coming from a normal distribution with zero mean. So that's our kind of null hypothesis. They're coming from a zero mean, but we don't know the variance. So the variance is going to be some quantity sigma squared. So first, let's assume that we did know the variance, and we're going to say, well, how would this mean quantity, how would this quantity be distributed under the null hypothesis that it was coming from a distribution with mean zero, and let's say with this variance sigma squared. Okay, so that's easy enough to do. So we can say, well, xi is equal to 1 over n sum xi, and we're going to assume that the observations are independent and all identically distributed. So therefore, this is going to be distributed according to, again, also normal distribution, because sums of independent normals are also normally distributed. The mean is still going to be zero because it's going to be the average of the means of the individual points. And now the variance, well, we've got the sigma squared, of course. We're dividing by n, so that's going to divide the variance by n squared, because that's how multiplying by constant works. But because we're adding up n independent data points, we also multiply by n, right? So we're dividing by n squared. So we're dividing by n squared due to this, and now we're multiplying by n because we're summing up n data points. Okay, and so now this thing is going. So this is the same as normal 0 sigma squared over n. Okay, so that's how that mean statistic would be distributed. And so we can just then, the natural thing is then to just normalize this. We say, well, we're going to make a new, let's call it x bar prime, and we're going to divide this by the standard deviation. Right? And right now we're assuming we know what the variance is. So we'll oops, that's a little bit too small. So, okay, and so now this quantity, what I meant is equal to this divided by, right? We're just going to normalize it. And so now then this quantity is going to be distributed as normal 0, 1, so a standard normal. And then what you can do is then you can just then compare. You can say, well, if my data is really coming from, this distribution, after I normalize it in this way, well, then the distribution I would expect for the mean is going to be 0, and that this is supposed to be symmetric. And then I can compare, my actual, let's say my actual x bar prime to that distribution and say, well, under the null hypothesis, it is the probability of getting a value this extreme is so and so, and that gives you kind of a p-value. And that that's how you would use it, and that's kind of how many of you, I expect, have already used it, and I've used it in the past, and there's other variations on it. But now the interesting thing is, and kind of the connection to what we're going to talk about, the connection to the way Bishop's going to introduce it, is what if you don't know the variance? So the natural thing to do then is to compute the t-statistic, which is exactly the same. But all you do is you replace the variance. You don't know the variance in that case. You replace it with the variance that you compute from your data. So you take your data and you compute it. So maybe we'll index this by n, still divide by n. And now it turns out that this thing has what's called a t-distribution. We'll see what that looks like in a second, with n minus 1 degrees of freedom. And what's interesting about the t-distribution compared to the normal distribution is that it can have heavy tails. So that means the normal distribution, once you're far enough away from the mean, it's kind of the values, you're basically unlikely to get values that deviate too much from the mean, let's say. Whereas for t-distributions, certain flavors of t-distributions, you can actually get values that are very large, essentially very far from the mean, to the point that, so for certain versions of the t-distribution, you can't even compute you can't compute the variance. They don't have a variance because you get these very large. You have the possibility of having these very large values, and you might think, well, that's what's the use of having such distributions? And one of the important uses that Bishop is going to talk about in this section is using these to do regression, to kind of deal with outliers in data, to deal with a situation where you might have 100 data points, but maybe 2 of them are really far out, and that in real life that happens, and you don't necessarily want those points way out there to affect the results of your analysis. So the t-distribution, by allowing large values, values that deviate from the mean like a lot more than they do under the Gaussian distribution, kind of allows you to kind of handle those cases more robustly. So that's kind of what we're going to talk about. So let's get to it. So, okay. So what does he say? So he says, look, we have seen that the conjugate prior for the precision of a Gaussian is given by a gamma distribution. So go back to section 2.36, the previous section, if you need a refresher on that. Now he says, okay, if we have a univariate Gaussian, so this is kind of think of, like what we have now, together with a gamma prior, and this is a prior on the precision, and we integrate out the precision, we obtain the marginal distribution of x in the form so and so. Okay, so why would we ever want to do this? So he's saying that, look, so essentially what he's saying is, look, you have data, you don't know the variance of it, but or the precision in this case, 1 over the variance, but you have some prior information about what that variance could be, and you're interested in the distribution of your data. So you know the mean, but you don't know the variance, and you're interested in the distribution of the data. So the thing to do is to just, and this is kind of the Bayesian thing to do, is to integrate over your uncertainty. So you have your normal distribution for a given variance, and you have prior information on how likely that variance or that precision is going to be. And so you can use that to essentially add up contributions from all the normal distributions at each of the variants, weighted by the prior probability of that variance or precision. So you can think of this. So you can think of this, and it actually, it's not just a way to think about it, it is what it is you are adding up the contribution, you're averaging a bunch of Gaussians, weighted by the probability of a particular precision. So, another way, just a very similar way of saying the same thing is, like, if you knew what the variance was, or the precision, you wouldn't need to do this averaging process, right? You would say, well, it's just normal x given mu and my precision tau, or my variance tau over -1. But since you don't know what that is, what you have to do is you have to add up the contribution from all different precisions according to the probability of each particular precision. So that's exactly what this is. So he'll call this an infinite mixture of Gaussians. That's another way of thinking about this. But maybe a more kind of palatable way of thinking about it. Just think about this as a probability. So this is a probability of tau, and this is of your precision, and this is your normal distribution given mean, and I didn't need to rewrite it. So you're just weighting up d tau. So you're just averaging all possible Gaussians with the same mean, but different precisions according to a particular probability distribution on each one of those Gaussians, given by the parameters of your gamma distribution, A and B. So you need to know what those parameters are. But once you know that, then you can just get a distribution on your data points. And it turns out that that distribution has the student's t is distributed according to the student's t distribution with a parameter called the degrees of freedom. So that's kind of the connection. That's one connection, right? So in the when we're doing the t-testing, we don't know the variance, so we compute the empirical variance, the variance of our data, and use that to compute the t-statistic. And here we're kind of integrating out the variance. I wanted to kind of make the connection more explicit. I didn't have time to do that, so an exercise for you folks out there would be to actually connect the two explicitly. So go and show that when we have data like this and we compute the t-statistic, it is indeed distributed like how he says here. So that's kind of a fun exercise. Probably not the easiest exercise, but I also don't expect super challenging. So if you want to have some fun, have some time to spare, that might be a good one to look at. Okay, so let's get back to the story. So right, so we've got the distribution. So we have a distribution on data points given the mean parameters of the prior, but no precision. We've integrated out the precision, and we have just the according to the probability of given by the gamma distribution, and then we get this this crazy looking function, which can't give you much more intuition for it. We just look, what does it have? Well, there's something being kind of exponentiated according to a. There's this looks like a kind of a mean quantity in there, so the deviations are relative to the mean, and there's some offset. So I can't give you any more intuition than that, I think. By convention, we define new parameters given by nu is equal to 2a, and lambda is a over b, in terms of which here's another form, and this is known as student's t distribution. The parameter lambda is sometimes called the precision of the t distribution. The reason we'll see in just a second is because, and as in certain parameter settings, it actually does become the precision of a Gaussian distribution. So even though it is not in general equal to the inverse of the variance, so it means the variance of the student's t distribution, the parameter nu is called the degrees of freedom, and its effect is illustrated in 215. For the particular case, nu equals 1, the t distribution reduces to the Cauchy distribution. This is the one that actually has no variance, because you get these extreme values a lot. And now while in the limit, so as the degrees of freedom goes to an infinite, the t distribution becomes a Gaussian with mean mu and precision lambda. So it's kind of like as you get as the degrees of freedom become very large, this t distribution tends to be a Gaussian. Then in that case, then the precision of that Gaussian is lambda. Now, this degrees of freedom idea, actually, it's kind of interesting to connect it back to kind of give you some sense of what that's about. That's just when you're computing, when we go back to our example here, when we have our data points, the degrees of freedom is n minus 1. And so essentially what this is saying is that if you have tons of data points, imagine you have 10,000 data points, then you're going to have a pretty good estimate of that of this empirical variance. So your t distribution, for many degrees of freedom, is basically going to be Gaussian. But if you have a very small number of data points, well, your variance could kind of swing wildly, and so that will all of a sudden make it possible to kind of have very large values in this t. Maybe your by chance your sigma squared, where you computed over 2 data points, is very very small, and so all of a sudden you're scaling things by a standard deviation computed over 2 data points, got a small value, the bottom is small, the top becomes very large. But if you have lots and lots of data points, then things are going to be basically well behaved like a Gaussian. Don't just think of it. This is one. I believe this is one exact way of what it is. This is basically the number of data points that went into estimating your standard deviation. So the more data points you have, the t distribution tends towards the Gaussian. The fewer you have, the more you start getting these heavy tails. Okay, so let's have a look here, just to kind of give you a sense. So, and as before, you can have as we saw with the gamma distribution, where funny stuff happens when a is less than 1 or whatever it was. So let's just start when you have infinite degrees of freedom. You have a nice Gaussian. When you have 1 degree of freedom, and notice how. So all of these are the same. All of them have mean 0, but notice how this Gaussian is now the probability of getting a value of 5 for this particular Gaussian is essentially 0, but for these guys, it's still very large. And for this guy, it's still really large. It doesn't look like it's gonna, hit anywhere close to 0 anytime soon. So it is kind of, kind of what, when we're speaking casually, this is kind of what we mean by these heavy tails, kind of heavier than the Gaussian, decaying kind of more slowly as you go away from the mean than the Gaussian does. Okay, so that's what we're talking about. From 2.15, we see that the student's t-distribution is obtained by adding up an infinite number of Gaussian distributions having the same mean but different precision. So that's what we spent a few moments talking about, right? We're adding up the contributions from an infinite number of Gaussians, because we're doing an integral. Infinite number of Gaussians. They all have the same mean, but they have different precisions, and we've weighted them a particular way according to our gamma prior. So this can be interpreted as an infinite mixture of Gaussians. We're going to be talking about this in a few sections. And the result is a distribution that in general has longer tails. We've been talking about this longer tails business for quite some time, as was seen in figure 2.15. This gives the t-distribution an important problem called robustness, which means that it is much less sensitive than the Gaussian to the presence of a few data points, which are outliers. And so he's got a really great picture of this. So let's look at that. So I'm going to kind of zoom in here. Make sure you guys can see. Well, anyway, I think, yeah, okay, that's good enough. So what we've got here is we've got just a bunch of data points. And if you zoom in, you can see that, and he's fitting two functions too. He's fitting a student's t-distribution, which is the red one, but underneath it is he's also fitting a Gaussian. And because this data is actually coming from what looks like a Gaussian, and the student t has the Gaussian, that's kind of a special case when you have an infinite degrees of freedom, both the fits are lying on top of each other. And now the cool thing that happens is when you introduce a couple of outliers here, there's 3 outlier points, and all of a sudden the Gaussian fit is now it has to, like it says, look, under the Gaussian distribution, I can't have values that deviate too far from the mean. And too far, what are the units of too far? Well, they're measured in units of my standard deviation. So the only way that I as a Gaussian can account for this clump of data and this clump of data is to shift my mean a little bit over and try to increase my variance so that this data is not so unlikely. So that's kind of what happens. So the Gaussian kind of shifts a bit and tries to accommodate these additional data points by that shift of the mean, but also most obviously by increasing the variance. So that's the only way me as a Gaussian can account for it. Whereas if you look at the t-distribution, it's not so phased, it's not so perturbed by these few data points. It says, look, under basically the distribution I was before, I can still, there is some possibility of observing data points. So I don't really need to shift very much. So you can see the mean is basically where it was before. It hasn't been affected so much by those outliers. So that's kind of I think the interesting robustness property that comes from the t-distribution. So so what did he say? So the effect of compares the maximum likelihood solution for Gaussian and the t-distribution. We find the t-distribution can be found, the maximum likelihood solution for the t-distribution, so the degrees of freedom, the mean, etc., can be found using the expectation maximum algorithm. This is a very important algorithm. We're going to talk about it in many chapters forward, but a very, very important algorithm. Here we see, but right now, what we want to discuss about right now is just the effect. So you get the kind of the big picture of why this t-distribution is useful. We see that the effect of a small number of outliers is much less significant for the t-distribution than for the Gaussian. And now, where do these outliers arise? Well, sometimes the underlying process corresponds to a distribution that has heavy tails, which can happen in lots of real settings. In real life, most data is not Gaussian, so you should be prepared for non-Gaussianity and heavy tails. Or simply through mislabeled data. So maybe that's kind of what's going on here. It's also an important property for regression problems. The least squares approach to regression does not exhibit robustness because it corresponds to maximum likelihood under a conditional Gaussian distribution. So I think what he's talking about, and especially in earlier sections when we talked about this, is under in the regression settings, we said that the probability of a data point of yi given I don't know, what was it, the weights, and some was normal with W transpose X being the mean, and it was Gaussian. So you kind of assume that your data points are situated around some mean with some variance, and everything is normal. And on that normal distribution, you're not going to get these robustness properties because you're basically ruling them out. You're saying that my conditional distribution is normal, so the only levers you have to play with are the variance and the mean. Whereas with the t distribution, you have kind of this degrees of freedom that allows you to account for robustness. Okay, so what he's saying then is that by basing a regression model on heavy tail distributions such as the t distribution, we obtain a more robust model. So that's just what we've been talking about. And then he just does some stuff, I guess, we're generalizing this to higher dimensions, just kind of change of variables. So we'll go through it. I don't know, don't have much to say about it. So if we go back to 2.158, which was this, and substitute the alternative parameters nu equals 2a, lambda equals a over b, and eta equals so and so, the t distribution can be written in this particular way. Okay, great. We can then generalize this to a multivariate Gaussian, so and so. So now we have vectors. This is a vector, and your precision is now a precision matrix. To obtain the corresponding multivariate student's t distribution in the form this. So again, you have your Gaussian prior on the scaling of this precision. So this is just your standard scalar gamma prior, and then you have your multivariate normal distribution. So it looks like what's happening here is that you've got the mean, you've got the precision, and this gamma is kind of scaling that precision, and you don't know what that scaling is. And so as before, you just average over all the scalings according to your prior on them. So okay, so using the same technique as for the univariate case, we can evaluate this integral to give this interesting looking distribution. Whereas now our d squared is our distance from the mean multiplied by the precision. This is kind of Mahalanobis distance. We'll talk about this. I don't know if we've already talked about it. It'll come up again. And this is the multivariate form of the student's t. Okay, so yeah, I don't know. Maybe this will become more important later on. So yeah, it's just here. I don't know, what, whether it's worth spending any time on. So let's just leave it at that. But yeah, so I think that's basically all I wanted to talk about here. So the student's t distribution is kind of very useful. It's really useful to know about this concept of heavy tails, where they can come from. This idea of the infinite mixture of Gaussians, I think, is very cool. But it's nothing more than just averaging Gaussians, averaging averaging the Gaussians that could be going into our data according to the probability of each of them given by our prior. And these kind of heavy tail distributions are very useful for just modeling data, but also accounting for giving our models a bit of robustness to outliers. There are other ways of doing it as well. Maybe we'll talk about those as we go when we talk about regression. But this is one way. So yeah, so hopefully that was useful. Hopefully the connection also to t-tests was useful. Maybe give you some insight. And yeah, if you want, just try to have a crack at trying to connect this to this. I expect not an easy task, but I think it'll be a useful one. Very good. So hopefully, yeah, just please, as usual, leave comments if you don't understand anything. If I made a mistake, please post, and I will fix it, and we can all learn together. I think that'll be great. And next time we're going to be talking about periodic variables. There's a very big section on periodic variables, very useful, and so we'll go through that together. So thanks for watching, and see you next time.